Our first speaker in this session is Professor Reinhard Genzel from Max-Planck-Institut for extraterrestrische Physik. More than anyone else, he has been in the forefront of research to establish a supermassive black hole in our galaxy. So our galaxy has its own supermassive black hole. Now, where is it? We'll learn from you. Please.
Thank you very much. I hope it will work. It does. Great. Well, we've heard already about strange worlds, extrasolar planets of a type we've never seen before, neutron stars, and now we take the last step into the abyss, namely supermassive black holes. May I have the first slide? Excellent. It does work. Now, of course, you know that supermassive black holes, or black holes in general, have been very well known to the general public and have been thought about by many people in science fiction. What I want to show you today is that black holes really is a serious subject of scientific investigation. And in fact, the story I will tell you about the next half hour is that a species of such black holes, namely so-called massive black holes with masses of millions to billions of solar masses, seem to be present very frequently in galaxies at their nuclei and play an important role in the evolution of galaxies. Now, before I tell you more about black holes, let's first take a step and show you a movie which we can nowadays do. Take a trip across the Milky Way and out of the Milky Way. Can we have the lights down just a little bit because it's a dark movie? Thank you. And here we are flying through the plane of our Milky Way, seeing some of the nebulae, these red nebulae where stars are still forming in our galaxy. Now, our galaxy is inhabited by hundreds of billions of stars like our sun, as you've already heard. And it's a fairly old object, we know, although still stars are forming. We live in a galaxy which is mostly a disk of stars, a rotating disk of stars, which you can see here. But if you fly out of this Milky Way at a speed of 10 to the 12 times the speed of light, you can see there's a central, very bright region, the nucleus of our galaxy. These island universes, which make up only a small fraction of the mass, as you've heard already, are the building blocks of the visible stellar light in our universe. These galaxies have masses between about 10 to the 10, so 10 billion to several hundred billion times the mass of the sun. He'll be flying through some of the nearby galaxies. And of course, we would like to understand how they have formed. When did they form? What were the processes involved? Now, some of these galaxies are clustered in big galaxy clusters. This is the nearest such cluster, where there are sometimes very massive objects, like this very massive elliptical galaxy in the center, M87. And the story which I will tell you about is that we now know that most of these galaxies, most of the massive galaxies in our nearby neighborhood, in fact, have massive black holes at their centers. And we can now sense these massive black holes and understand how they are related to these galaxies. But let me first take a step back and say a little bit more about black holes. The first one who speculated about objects one would call a black hole was Reverend John Mitchell in Cambridge, already 150 years before really the theory of general relativity was developed. He asked the question, if you had an object of the mass of the sun and compressed such that the escape speed from the surface of that object reaches the speed of light, how big would that object be? And the answer is 3 kilometers. So that's still a little more compact than the neutron stars we've heard about. If you do the same thing with the Earth, it would have a diameter of 1 centimeter. So these are very compact objects. But in fact, after this speculation, not much note was taken of. It took much longer until a proper theory of gravitation was developed, as you well know, by Einstein, 1915-16, and the first solution of the so-called spherically symmetric case by Karl Schwarzschild 1 year later. And since that time, of course, relativists have theoretically probed and understood these difficult equations of general relativity. Roy Kerr, 50 years later, solved a rotating case, so a black hole which has a spin, a rotation, and there's also the possibility of a charge. Now, these are the three numbers which general relativity tell us we need to understand black holes: the mass, the charge, and the spin. Now, astrophysical black holes generally probably only have two of these numbers in any significant amount, namely a mass and a spin. Now, there are more complicated effects we can think about having to do with gravitation and quantum theory, and also the issue of thermodynamics. And Stephen Hawking has led the way into this very difficult area. Now, Hawking radiation, which is a process by which, in fact, radiation can escape from a black hole, unlike what you would have expected from the black hole solution, which has an event horizon size, which scales with mass. And inside of the material or anything inside of the event horizon size cannot communicate with the outside. Hawking showed that at the surface, if you like, of that black hole, in principle, uncertainty principle allows you to communicate with the environment. But this Hawking radiation does not play a role for the black holes in the astrophysical environment. That might be something for very small things, very small black holes. So black holes are objects where light cannot escape, but now I'll tell you that paradoxically, you can think of black holes also as the most luminous, the most efficiently radiating objects. And that is because as gas or stars or rocks or humans, if they are unlucky, fall into a black hole, just before they disappear inside the event horizon, the gravitational energy, which is very large, can be released, lead to heating up of the material and to radiation. And that radiation can be extremely efficient. In the extreme case of a maximally rotating black hole, it can be about 50% or almost 50% of the energy mc squared. And in that sense, theoretically speaking, black holes can be the most efficient sources of energy we can think of. And you will see why that might be important. So that's theory. How did black holes come into the astrophysical environment, and how do we think they might be there? Now, that started to happen in the 1960s, so over 40 years ago, when radio astronomers, in particular in Cambridge, England, started to discover objects which, in their radio maps, were relatively bright objects, but which had only feeble counterparts. Here's one such object, 3C273, one of the early ones. And you see on this optical picture, there's a star, or something which looks like a star. So these objects were called quasars. And it was Martin Schmidt at Caltech who then discovered, by looking at this star in optical light with a spectrograph, that there were emission lines. And these emission lines were systematically shifted to the red. And already at that time, it was known, of course, that the universe is expanding. So if you take the expansion rate of the universe and that redshift, then you learn that this object is very far away, at least for standards at that time. And if you then convert this little speck of light into a total energy production, what comes out is that this quasar produces about 10,000 times more energy than an entire Milky Way. Now, an entire Milky Way is fueled by hundreds of billions of stars. So the question is, could it be that such quasars are powered by yet more dense and compact concentrations of stars? Now, modern images of quasars like this one, nearby images with the Hubble Space Telescope, show us that, without exception at this point, quasars are the compact, very bright, often unresolved nuclei of big galaxies. So can we interpret this light concentration here as a concentration of stars? Now, considerations which were made in the 1960s by Lindenbell, Rees, Salpeter, and Sunyaev and Zeldovich led overall to the picture that no, normal fusion, as efficient as it is for stars and entire Milky Ways, is not sufficient to explain quasars. At least not if quasars live any length of time. So what could be more efficient? Well, I've given you already the answer. It could be accretion of gas onto very massive black holes. Black holes of masses of about 100 or million solar masses or more. And I told you already that energy creation there, in principle, theoretically, can be very efficient. And so that picture of accreting black holes being the source of the quasars grew in recognition and acceptance amongst the astrophysical community over several years and decades, with additional evidence supporting it. For instance, very high energy radiation, X-rays, gamma rays, variable emission, which all tell you that there had to be a very energetic process in these objects, and that it had to be very small. Also, spectacular jets, that is, collimated streams of ionized material making radio emission, synchrotron emission, streaming away at essentially the speed of light from such objects show you that they are very energetic processes. So within the radio optical observer community already in the 1980s, generally speaking, most people accepted the black hole model. But of course, is it true? And what would you have to do to really prove it? Well, in the end, of course, general relativity predicts an event horizon and predicts that the source of such a black hole must be a very massive object. So the proof, really, an unambiguous proof, would have to be that you determine the gravitational potential of such a quasar to be a concentrated object with an event horizon which is predicted by general relativity. Now, that's a tall order. That proof is very difficult to do because if you think of the sizes which you would have to measure at the distances of the quasars, which are very far away, that is not possible, even with modern technology at the present time. So you have to be a little more sufficient by going to nearby objects, and you will see how that is done. Now, we are celebrating Galileo, who took a new device, a new technical device which had come about, and looked at the sky and made great discoveries. We're still doing this in astronomy. And the development of technology and experiments plays a very big role in our discoveries. For the search and studies of black holes, a whole set of machines, much bigger, of course, than Galileo, play a role. We are observing with big telescopes on the ground, as you saw this morning, a whole slew of 10-meter class telescopes. We're using the space telescope, which gives us sharp images in space, and we are looking at other wavelengths, radio wavelengths, for instance. We are looking at X-rays, and we are looking even now at the hardest gamma rays from the ground and detect objects which might be such accreting black holes. So these are our modern guns we use to study the phenomena and tell us about these mysterious objects, and which indeed, in fact, are crucial to carry out or come close to, carrying this proof which I told you about, to make measurements of the gravitational potential. Now, one object in particular has been very helpful in this attempt, and that's, surprisingly perhaps, our own Milky Way. Our Milky Way is not a quasar, by no means, but is so much closer by a factor of 100,000 than any other very bright object like a quasar. We are only 25,000 light years away from the center of our Milky Way, and perhaps we can hope that at a small level, the same kind of physical processes which also happen in quasars would happen in our Milky Way center. Why not? Maybe there is, and that was a speculation already in the 60s by Lindenbell and Rees, there might be, a smallish, perhaps, central black hole in our Milky Way. And indeed, early measurements in the 60s and 70s were beginning to show some interesting things which might point in this direction. Now, I should remark, there's one difficulty. The center of our Milky Way cannot be observed with visible light. And that is because between us and the center of the Milky Way is the entire disk, which is full of stars. That's not so bad, but it's also full with interstellar gas and dust. And the dust extinguishes the optical light by a large factor. So you have to observe the galactic center. That makes it more difficult at long wavelengths in the radio and at short wavelengths in X-rays and so forth, or perhaps also in the infrared. Nowadays, with modern infrared, that is wavelengths which are, say, 4 to 8 times the wavelengths of visible light, you can look at our own galactic center and you see the stars here forming a very dense cluster, nuclear cluster, in the central, light year region around the center. The radio astronomers, which you see here on the right side, observe the galactic center with interferometers. That is, antennas, radio telescopes, which are separated by large distances in order to get very good resolution. And they find that there is gas, hot gas. This is this extended-looking radio emission here. But surprisingly, there is a compact, extremely compact radio source. We now know from so-called intercontinental interferometry, a very long baseline interferometry, a very powerful tool, that this source is only a little bigger than the sun. So it's a very compact object. And perhaps, that was the speculation, this might be the site where the center of our Milky Way is, where everything rotates about, if you like, the deepest point in the gravitation potential, and maybe that could be a black hole. Now, how do you prove that there might be a black hole? Well, think of what Kepler did. Kepler took Tycho Brahe's measurements and looked at these measurements and found that, in fact, the planets were moving around the sun on elliptical orbits. And the average speed, around orbital speed of the motion of the planets goes like 1 over the square root of the distance from the sun. Now imagine, in a thought experiment, that the sun wouldn't shine. And imagine that the work of Newton, Einstein, and Kepler is available to us, and the measurements of Tycho Brahe. What would we conclude? We would conclude that there's an object in the center of the solar system of 1 solar mass, just from the measurements of the motions of the planets, without, in fact, knowing that the sun is shining, because we don't see anything. So we use test particles, planets, and in the case of the galactic center and other galaxies, gas and stars, to see something which we cannot see with our telescopes. We see it through their impact on the motions of the nearby stars and other objects. So that is something which, in fact, Charles Townes, Nobel laureate for the invention of the Meson laser, began doing in the 1970s with his group. What he did, he looked at a emission line from probing this extended radio emission here in the infrared at 10 micrometers wavelength. So that's about 20 times the wavelengths of light. And he took these spectra here in these different apertures, and what you see is that the spectra move around. They have different positions around here, so the wavelength changes. Now that tells us that there's a motion, because the changes in wavelengths, as Jocelyn Bell-Bonnell already showed us vividly today, produces a Doppler effect. And that Doppler effect, in fact, is why these things are moving around, and the motions are very large. Remember, the Earth moves around the sun with 30 kilometers per second. Here we're talking about hundreds of kilometers per second. And so that tells us there must be some substantial amount of material in this region, although the stars, which we can see, would not be able to account for this. So Townes, in the early 1980s, concluded with his group that there might be a massive black hole there, and he said that mass would be around 2 to 4 million solar masses. Okay, so that was 1980, and we have now almost 30 years passed since that time. What is the answer we have now? About 4 million solar masses, okay? So Townes was right, but between what he did at that time and what we now can do is a big difference, very big difference in terms of what technically is possible. We can now use these big machines, for instance, the big telescopes on the ground, and use so-called adaptive optics to make very, very sharp images and see the stars in the vicinity of Sagittarius star move. actually move on the sky, and they move fast. That's what we find. And they move following Kepler's laws. That's what we also find. So there clearly is a central mass. The radio astronomers can also see motions in here. For instance, they can see the motion of Sagittarius star. And they find that Sagittarius star is not moving, so it must be heavy. One of these stars, in fact, we have now traced over almost 2 decades. And when you look at its position on the sky, these are these blue and yellow points from the 2 groups observing it, from the VLT and from the Keck telescope. This star is moving regularly around a curve, which you undoubtedly will recognize resembles an ellipse. An ellipse whose centroid, whose focus is right here, and that's the position of Sagittarius star, that radio source, that very compact radio source, which you suspected might be the culprit. So very clearly, this star orbits the galactic center source, Sagittarius star, just like planets move around the sun, and clearly shows us that there must be a compact object in the very center. And we don't only see one star, we see many stars. We, in fact, are tracking now hundreds of stars, and we see their motion. We don't have complete orbits for all of them, but we see that the central source, Sagittarius star, which then has a 4 million solar mass, is sort of the central hub, if you like, the nucleus of a swarm of stars in its vicinity. And there are very precision measurements possible now, which tell us that this object cannot be anything but a black hole beyond any reasonable doubt, as long as we accept general relativity. Because no other objects would fit in here, if you like. The stars coming as close as only a few light hours from the central object. So the galactic center is really an object where we can be fairly sure that there is a central black hole of about 4 million solar masses. But now, how frequent are these objects present elsewhere? Now, our nearby galaxy, Andromeda, also has a black hole, in fact, much bigger than our own, about 100 million solar masses. We can't be so sure there that it's a black hole, but if you accept the galactic center as sort of our best proof, it's very likely that this is a black hole. Radio astronomers using VLBI have a wonderful case on this object, which is a little more distant, that has a 10 times the galactic center mass in the center, surrounded by a little disk of gas, which they have observed with great precision to orbit around. So that is likely also a black hole. And M87, that last big object in our movie, also has a black hole. This one being a few billion solar masses. So these are very big objects. And in some objects, X-ray astronomers have been able to look with spectra at the motion of gas just in the very central region, the very hot gas, and they see gas swirling around some of these objects with a significant fraction of the speed of light. And that tells us that the mass there really must be concentrated on a scale of a few times the event horizon of a black hole. So that's very strong evidence. And the demographics now is that we are getting ever better investigations which tell us that almost every big galaxy in our neighborhood does have a central black hole. And surprisingly, that the mass of that central black hole, which is plotted on this axis in logarithmic units this way, scales with the mass of the galaxy it's embedded in. And that tells us that the two objects, the galaxy and the central black hole, are related to each other. And we suspect that is due to their common evolution. So when have they formed? When have these black holes formed? Well, probably very, very early. We can look back in time by looking back out in space. So when we are here 13.7 billion years after the Big Bang, we can look back in time and see that as we do so, the activity of star formation, the activity of galaxy formation in blue, increases by about a factor of 10 or more as we go to the early universe, say 2 or 3 billion years after the Big Bang. And right then, there was also a maximum of the activity of quasars. So the big black holes which we see around us in M87, these big elliptical galaxies, were formed then. We only see now their ashes. They were formed then when the galaxies were formed. And in fact, we can trace back now with the biggest telescopes to some objects which were formed already, this quasar here, only 800 million years after the Big Bang. That's a very, very brief moment on astronomical timescales. And we don't quite understand at the present time how these very massive black holes could have formed that early. And that's a very important point. And we suspect that the formation of these galaxies and the formation of these black holes is closely related. Galaxies were formed, as you've already heard, when in the expanding universe, the dark matter, the dominating material, was clumping in dense regions. Clump structures of these dark matters were sort of pots of local minima in the gravitational force where gas was falling in. And as the expansion of the universe went on, the densest regions became ever denser and grew in mass through a process called hierarchical mergers, as you can see here. And it's these large concentrations of dark matter then, which led to the concentration of baryonic material, so the normal material, and the formation of stars and galaxies. So over time, through this process, with a lot of these little clumps banging into each other, etc., big galaxies were formed. So the question now is, what does this have to do with the big black holes? How is the story of these growing galaxies over time connected to the growth of the black holes? And that is through the process which we call mergers. So from time to time, in the early universe more frequently than nowadays, two galaxies, two gas-rich systems, like in this simulation here, had the bad chance of having a traffic accident, to collide with each other. And in this collision, in fact, the two systems were completely disturbed. Material was flung out to large distances, and at the same time, material was brought into the central regions, and the end result was a big elliptical galaxy. And the gas, which was falling into in this process, could very well have formed big black holes. And this story we can actually see sometimes in real life. Up here, you have a picture of basically totally dissolved double system of two galaxies in these greenish colors. And here are two X-ray glowing central black holes, which is the process of this merging. At high redshift, we can begin now with the bigger telescopes to also see similar processes. So we now know black holes are frequent, they exist, and they have a very important role to play, although they only make up about 0.1% of the mass of a galaxy, because they inject energy and they interact with the galaxy they're embedded in. They play a very important role in the evolution of the island universes like our own. Thank you very much.